Hello once again, complex analysis students. Today we're going to talk about the Cauchy-Goursat Theorem. So what does the Cauchy-Goursat Theorem say? It says if you have a function that's analytic at all the points on and interior to a simple closed contour C, and the orientation is not specified here. It turns out it doesn't matter whether it's positive orientation or negative orientation. But if you have that set up for your function, then the integral, the contour integral around C of f of z dz works out to be 0. This theorem is actually quite hard to prove, and I think in the interest of time, I'm not going to prove it in its full glory. But if you assume an additional hypothesis for the theorem that f prime is also continuous at all points on and interior to the contour C, then it's actually not too bad to prove it. So I think I may give the proof with that additional hypothesis that f prime is continuous at all points on and interior to C. And it turns out a little bit later we'll see that anytime a function is differentiable at a point, that it is also all of its derivatives are differentiable. So this is a hypothesis that we can assume that it's not a big worry. It's definitely true that if f prime is analytic at all points, then also its derivative is continuous because its derivative is actually differentiable. So anyway, let's look at a proof under this hypothesis. For this proof that assumes this additional hypothesis, let's assume C has a parameterization. We'll call it z of t equals x of t plus I y of t, where the parameter runs between a and b. And let's assume that our parameterization is oriented in the positive sense. And then we'll suppose f is analytic inside and on C, and f prime is continuous inside and on C. Now from the definition of contour integral, we know that the integral along C of f of z dz is integral from a to b f of z of t times z prime of t dt. Now let's suppose that we've got f of z broken up into its component functions like so. Then just repeating what I said above here, we know that the contour integral along C of f can be written out like this. But now that we have f in its component form, we can write this as u of, but the x comma y are going to be the x of t and y of t from the parameterization of the curve. So you get u of x of t comma y of t plus iv x of t comma y of t. So that's f. Then z prime of t is x prime of t plus I y prime of t, all that times dt. Okay, multiplying all this out and then combining the real and imaginary parts, I would get u times x prime of t minus, then I'll get v times y prime of t dt plus integral a to b. So I'm doing the imaginary part and breaking it up into two integrals. Then I would get, let's see, u y prime of t dt, well, u times y prime plus v times x prime. And then up here in the upper right hand corner, let me remind you how differentials work. So if x is the function x of t, then dx, we can write that as x prime of t times dt. And similarly, if y is equal to y of t, then dy is y prime of t dt. So I want to make these substitutions here and here in these two integrals I have at the bottom. After I distribute the dt across the sums there, I can actually view this as integral over c. So the x prime of t times dt, that'd be u dx. And then I've got minus and then vy prime dt, that'd be minus v dy. Then I would have I times integral along c of, just to put the x's first, I'll put v dx plus u dy, like so. Now you may remember seeing integrals that looked like this back in your multivariate calculus class. All these integrals here are just regular old real valued things. They're regular old contour integrals. So we had a pretty name brand theorem that applies to this sort of thing, Green's theorem. Green's theorem says that if you're integrating clockwise something of this form, p dx plus q dy, you can actually convert it into a double integral involving the partial derivatives of those functions. And here, you got to assume that p and q have continuous first order partials on this region R, and R is the region that's enclosed by that simple closed curve. We have all that, though, in what we're doing because we were assuming that our function was analytic, and we also assumed that its derivative was continuous. And so if the derivative of f is continuous, well, we know that the derivative equals ux plus I vx, or you can write that as ui minus I vy. And that means that all those first order partials are continuous if f prime is continuous. So we have the setup we need to use Green's theorem. And so from the previous page there, we had calculated that our integral of f of z dz along c could be written out in this form. I left off an I there. Should be an I in front of that second integral. And if we apply Green's theorem to both of those integrals, okay, the one where it's u dx, this first one here, u dx minus v dy. So u is playing the role of p, and negative v is playing the role of q in Green's theorem. So this would be the double integral over the region surrounded by c, and then you'd have the qx would be negative vx, and then you have minus uy plus I times the double integral over that region R. And then on the second integral, v is playing the role of p and u is playing the role of q. So this will be ux minus vy. And these are dA, differentiating with respect to the area elements. But remember Cauchy-Riemann equations. We have in our hypotheses, we have what we need, that we know the function is differentiable, so we know Cauchy-Riemann is satisfied. So we know that ux equals vy, and we know that uy equals negative vx. And so when you apply the uy equals negative vx to that first thing there, you see that what you're integrating is actually 0. And when you apply the ux equals vy to the second integral, you see that what you're integrating there is equal to 0 also. So this tells us that our integral of f of z dz along c ends up being the double integral along this region R of 0 plus I times the integral around R of 0, which is a big whopping 0. And that proves what we want to prove. When you take away the hypothesis, though, that the derivative is continuous, we can't use Green's theorem the way we did, and so it makes the proof much more difficult. I do encourage you to read the proof, though. It's an interesting proof, and it uses techniques that I think are used more if you go on further in your studies of complex analysis. I think that sort of argument gets used in several locations. But in the interest of time, I just wanted to give you the short version of it here. Let me give you a quick example here at the bottom. If your curve C is just a unit circle, and it doesn't matter whether it's oriented positive or negative, if we want to look at the integral around C of the function z over e to the z, the thing to notice here, so that function z over e to the z is entire on account of e to the z is never equal to 0. So that function's definitely differentiable inside and on the curve that's the unit circle. And since the circle is a simple closed curve, this equals 0 by the Cauchy-Goursat theorem. I mean, that's kind of nice, because I don't know if we had to do that contour integral from scratch. I suppose maybe we could also find an antiderivative of it, but this is way easier, right? Just instant answer 0. So a little definition here. We say a domain D is simply connected. It just means that every simple closed contour in D encloses only points of D. So somehow you can't have a simple closed curve in D that somehow encloses some point that's in the complement of D, because that would mean that it essentially means that there are no holes in the domain. So simply connected just means no holes in D. For example here, on the left there, I've drawn a domain that has a hole, the little white spot in the middle. So that's not simply connected. Those points in the white spot are not part of D. And then you can put a curve that goes around that hole. So the curve is enclosing points that are not in D. And then in the right-hand picture, I'm trying to depict something that is a simply connected domain. So our set D here is just the first quadrant. So if you draw any simple closed curve in the first quadrant, it's only going to enclose points that are in the first quadrant, nothing outside of the first quadrant. So the theorem that we have here that relates to simply connected domains is that if a function f is analytic on a simply connected domain D, then the integral along C of f of z dz equals 0 for any closed contour C lying in D. So notice it's just closed is the only hypothesis about the contour. It doesn't have to be simple. So we could have a contour that is self-intersecting. If it were a simple closed contour, we're just talking about the Cauchy-Goursat theorem. It says that, if you've got an analytic function inside of a simply connected domain, if it were a simple closed curve, Cauchy-Goursat would give it to us immediately. So the idea of the proof of this one is that the proof could get complicated if the curve is self-intersecting an infinite number of times. But if the curve only self-intersects a finite number of times, like I have in this picture here, then the idea of the proof would be something like, well, if it self-intersected itself a finite number of times, then you could break the entire loop up into a number of pieces, let's say C1, C2, C3 in this picture, and each of those pieces are simple closed curves. And so then the integral along C of some function f of z, of our function f of z dz, which is analytic on the entire domain that contains C. So that means that f is definitely analytic on each of these curves, C1, C2, C3, and inside of them. So we could write this as integral along C1 of f plus integral along C2 of f plus integral of C3 along, or integral of f along C3. And then each of these integrals would be 0 by Cauchy-Goursat. But yeah, if we're talking about something that self-intersects an infinite number of times, which can happen, like if you took something like the curve represented by y equals sine of 1 over x, and then part of the curve would be along the x-axis, yeah, it could do something crazy. So we're not going to try to do the full proof of it, just this simple idea of in the most common situations. So let's look at a little example here. Okay, so the function that we're trying to integrate here, e to the z over z squared plus 4 times z squared minus 9. Well, when you look at the denominator, you can see where the problem points are. When what causes you to get 0 in the denominator. And I've indicated those points in blue in the picture on the right. Plus and minus 3 are where z squared minus 9 is equal to 0, and plus and minus 2y is where z squared plus 4 is equal to 0. Maybe I could give myself a domain that's like, avoids those, give myself a domain that avoids those zeros of the denominator of the function. And so I can see f is analytic here. And I can also see that D is simply connected. It's just a simple box. So I have a closed contour that is inside of a simply connected domain, and it's analytic there. The function that we're integrating is analytic in and on that curve C. So this thing that I'd be trying to integrate here is just equal to 0 by our previous theorem, since that function, f of z equals e to the z over z squared plus 4 times z squared minus 9 is analytic in and on C, and C is contained in D, where D is simply connected. I mean, we could have got that this was equal to 0 just by Cauchy-Goursat, but I just wanted something to try to illustrate how you might use Cauchy-Goursat. A nice corollary of Cauchy-Goursat is that if you have a function that is analytic on a simply connected domain, then the function f has to have an antiderivative on D. The proof is really simple. Under the hypotheses of this, we know that the integral along C of F has to equal 0 for every closed C in D. You may remember we had a theorem a while back that said if this condition is satisfied that I've just written down in green, and your function f is continuous on that domain, which we know it is because we're assuming f is analytic, which implies continuity, then we had this previous theorem that had three conditions that were equivalent. One of them was the integral is equal to 0 around every closed curve in that domain is equivalent to saying that the function has an antiderivative on D. So we kind of get this one for free by using a previous theorem. And then another corollary that we get almost for free is that entire functions always have antiderivatives. And the proof is very simple. Just observe that the whole complex plane is simply connected. So if you looked at any integral like this, where C is closed, so just take any closed curve, this is going to be 0 by the previous theorem. And then again, we have the theorem that says anytime integrals around closed curves is always equal to 0, then the function has to have an antiderivative. That was it's that three-part theorem where all the conditions are equivalent before. Okay, the next little topic here is multiply connected domains. So multiply connected just means not simply connected. And so that just means then, in turn, that multiply connected domains are domains having one or more holes in them. So it's possible in multiply connected domains, it's possible to have closed curves that go around points that are not in the set, in the domain. And so here's a big wordy theorem. I'm going to point to the picture in the lower right there as I read what this theorem says. So suppose you've got a simple closed contour with positive orientation. So that's that outer curve C that's containing that yellow region. And then inside of C, you've got a number of simple closed contours with negative orientation. So in that picture at the lower right, I've got C1, C2, and C3. Notice their orientation is going opposite of C's orientation. And all of these blue curves, C1, C2, C3, they're not intersecting with each other. So neither themselves nor their interiors are intersecting. Okay, so that's your setup, just that picture that you have in the lower right. Now, if you know that F is analytic on the part that I've shaded yellow there, so that would be the part that's on C or on the curve C1, C2, C3, and the region in between, but not inside of C1, C2, C3. Just on C1, C2, C3, and on C and in the yellow region that's between them. I realized in the thing I should have an intersection there. Anyway, if you have that set, so the function's analytic on the yellow region that includes the curves themselves, then the integral of f around C plus the sum of those integrals around the C1, C2, C3, that total sum has to equal 0. So let me give you the idea of how you would go about proving this one. So I have a second picture down here. So the idea is that if you can draw a polygonal arc from C that connects to C1, and I'm calling that L1 in red there, sort of on the left side of the picture. And then you can make an arc, basically a line, or maybe a polygonal arc, L2 that goes from C1 to C2. Then you can make an arc that goes from C2 to C3, and so on. And then when you get to the last one, you can make an arc from the last one. In my picture, it's C3 back to C. And you give those arcs L1, L2, L3 in orientation, direction. And then if you read around, so if you started on C and then went along L1, then partially along C1 till you get to where L2 picks up, then go from L2 to C2, then you can go in the positive direction around C2 to get to L3, then you go along L3. And if you trace that around, you get a curve gamma 1. Gamma 1 would be the curve that's formed from pieces of C1, C2, C3, and then those red arcs, L1, L2, L3, along with C to enclose that blue shaded region. And if you look at that curve that goes along L1, C1, then along L2, then along C2, then along L3, then along C3, then along L4, and then back around C to where L1 starts, that's a simple, closed, well, it doesn't even matter that it's simple, but it's a closed arc, and the function f is analytic in and on it. And so if I call that curve that we sort of pieced together from all these other curves gamma 1, then Cauchy-Goursat says the integral of f along that gamma 1 is going to be 0. And then similarly, if you go around sort of the bottom half of C, and then you go sort of backwards along L4, and then go along C3, and then go backwards along L3, and then along C2, and then backwards along L2, then along C1, and then backwards along L1, and then back around C again, you get the curve gamma 2 that encloses the green region in the picture. And because that's a closed curve and the function's analytic in and on it, then we get the 0 integral again here too. But then the kicker is that, because you trace along the L1 both forward and backwards, and then you trace along L2 forward and backwards and so on, all those little red bits end up canceling out. So if you do the integral along gamma 1, and then you do like plus gamma 2 of f, and then you break that up into all the little subarcs that you get for doing gamma 1 plus gamma 2, it ends up just canceling. All those little L1s and L2s cancel out, and you're just left with C, and then C1, C2, and C3. And so, but we already said that, the integral of f along gamma 1 plus gamma 2 would be integral along gamma 1 of f plus integral along gamma 2 of f, which we know is 0. So that's the gist of the proof. It'd be a lot of trouble to set it up where you're really showing how all those things cancel out. But I think that it would be a good exercise for you to see how you go from here to here. But the crux of it is that the L parts cancel off. Okay, this next corollary, which is called the principle of deformation of paths, probably is the more important result, and it's a specific instance of the previous theorem is all it is. So it says you've got C1 and C2 are positively oriented, simple closed contours, and C1 is going around on the interior of C2. So C2 is the outer one, and C1's the inner one. And then we have a function f that's analytic on both of those curves, C1 and C2, and on the region in between them. Then turns out that the integral around C1 equals the integral around C2 of f. It's called the principle of deformation of paths because we can kind of imagine that we're able to continuously deform the outer curve until you get the inner curve, right? Like I could take the outer curve and just sort of start shrinking it in a bit, shrink it even more, and so on until you shrink the outer one to the inner one. Or vice versa. You could start from the inner one and sort of expand it outward. And any of the curves in the middle are going to give the same integral when you integrate f around them. And the reason that this is true, it follows immediately from the previous theorem. We know that the integral around, let's say, C2 of f plus the integral around negative of C1 of f. I'm putting negative on the C1 because in this setup, in our corollary, C1 and C2 have the same orientation. So if I put a negative on C1, it has the opposite orientation. And the previous theorem says that would be 0. And then, of course, this is the same as saying the integral around C2 of f minus the integral around C1 of f equals 0. And then the result follows immediately, right? Let me give you an example of how you might use that. So in this picture down here, I've got C2 is just a circle centered at the origin of radius 4. And then C1, the blue square-shaped contour, it's just the square, it goes through 1 on the x-axis and I goes through 1 and negative 1 on the x-axis and I and negative I on the y-axis. So it's just a square of side length 2 centered at the origin. So if I were to integrate this function z plus 2 over sine of z over 2 around C1, it would be the same as integrating that function around C2. Why are these integrals equal? Well, if you think about the previous theorem, as long as we knew that the function that we're integrating is analytic on both of those curves and in the region between them, then we'd have it. This function f of z equals z plus 2 over sine of z over 2 is analytic on and between c1 and c2. Why is that? How do you know that that function is analytic? Well, we know where the zeros of, like this function being composed of analytic functions, the numerator is analytic everywhere, and the denominator is analytic everywhere also, so the quotient will be analytic everywhere except for where possibly the denominator is equal to 0. And we know sine of z over 2 equals 0 if and only if z over 2 is a multiple of pi, so n times pi. And then this is true if and only if z is equal to 2 times n times pi. So the only places where we get that we'd be getting zeros in the denominator, let me indicate them in red in the picture up here. Well, we have at the origin, when z is equal to 0 would be a problem place, but that's not in the region between or on the curves. And then the next one after that would be, like you'd get negative, like you'd get plus and minus 2 pi. Well, 2 pi is out here at like 6.28, right? So if I extend my axes out a little bit further, so here's 2 pi and negative 2 pi. Those points are also outside of our region. So the bad places, the red dots, don't fall in the yellow region. So we know that our function is analytic on the yellow region, and then we get that equality at the top there by the previous theorem. So that's an example of the principle of deformation of curves. It wouldn't have mattered, I mean, the square and the blue square and the green circle are two examples, but it could have been any curve in here like this that's going around like that would have the same integral. So that gives us some flexibility when we want to compute integrals. If we know we can deform the curve to something that's easy to integrate around, that might be handy. So this brings us right up to the next big fact about contour integrals. This is going to be the theorem that we use the most to compute values of integrals. It's called Cauchy's integral formula. So I'll go ahead and stop this lesson here, and we'll pick up with Cauchy's integral formula for the next lesson. Talk to you again soon. Bye now.